In this section of communication systems, we'll be talking about communicating over long distances via waves. In the previous lectures, we talked about being able to communicate over long distances through a wired connection, from the early examples of a telegraph, then moving to the telephone and telephone wires. But now we're going to look at being able to communicate over long distances wirelessly. Have you ever thought about how we're actually able to transfer information, let's say from a wireless access point down to your computer? I mean, how is it that all of that information that we might find on the internet or the computer, where it's able to just fly through the air somehow and get to our computer? And so that's what we're going to be looking at today. Well, this is all made possible via electromagnetic waves. And it was first, discovered by James Maxwell in the 1850s, where he found that an electromagnetic wave could be produced by rapidly changing the current direction in an electrical circuit. This was further solidified by Heinrich Hertz, Hertz being the frequency measurement, in 1886, who then developed an oscillator. And what an oscillator does is it rapidly changes the direction of current, which then creates a magnetic field, and as that magnetic field is produced, it pushes it, breaks it off into space, and therefore creates an electromagnetic wave. And so it is through these types of waves, electromagnetic waves, that we're able to do all of the different types of wireless communication that we do today. So we're going to kind of take a basic look at what these waves look like. And this will really be just a touch on the surface, and in your physics classes or physical science type courses, you really go much more in depth. But I certainly want you to be familiar with how these waves work and what they look like, in a sense, because they are so critical to our modern society and our ability to communicate over long distances. So an electromagnetic wave is produced when a magnetic field is pushed into the air, which induces an electric field in the atoms of the air. And then it's a continual action from there. So we can use an oscillating machine here, an example of an oscillator on here, which again takes current and switches it back and forth very quickly. And as that current is released, it creates an electric field in the atoms of the air, which then produces a magnetic field. And as you kind of see in the picture here, basically as one initiates, the other is a result of it. So if we start with a magnetic field, the result is electric field in the atoms of the air. Then those electric fields then produce another magnetic field, and so forth and so forth. So it's a back and forth from magnetic to electric, a continual action that goes on for quite some time. The power of this is that we were able to find that we could actually put information on these waves and send them across the air. So the magnetic waves work like a sine wave, which looks like an S and goes back and forth. And when we look at these waves, we talk about their wavelength and the wave frequency. Obviously the wavelength being the horizontal length, but then the wave frequency being the vertical component of the wave, which is the measure of how many waves are produced in 1 second, which again, as we talked about before, we measure that in hertz. So electromagnetic wave actually travels, or we've found that it travels at the same speed as light, which is 100,000 miles per second. So these waves travel very, very, very fast, and it depends on the hertz, the frequency of these waves, in terms of the types of information that we can put on them, and how fast and how far they will travel. Here you kind of see an example of the electromagnetic spectrum. Again, this is something you would really look into in a physical science course. So across the top you can see the different wavelengths from a radio, which is 10 to the third power, and moving into the microwave, infrared, visible light is kind of in the middle of the spectrum, and then moving over to the right, ultraviolet, X-ray, and gamma rays. So each of these rays have different components, they have different wavelengths or frequency, and each of them can do different things for us using the different technology that we have. So as I mentioned before, we can use a process called modulation to put information on a wave. One of the first ways that this was used was with amplitude modulation and frequency modulation. You're familiar with the term AM radio or FM radio, which all goes back to the type of information put on this electromagnetic wave. So in amplitude modulation, we change the height of the wave, which is why we call it amplitude. Whereas with frequency modulation, FM, we change the frequency of it. And depending on how we change either the amplitude or the frequency, we can get different types of information, and it can be transferred over the airways in different ways. So with the radio was the first way that we really were able to do this. And so radio was the ability to communicate using electromagnetic waves. As I mentioned, radio waves or electromagnetic waves travel at the same speed of light. Light waves, however, are much higher frequency and don't require a medium to travel on, meaning that light waves can transfer or travel, let's say, through space, for example, whereas electromagnetic waves need some kind of medium to transfer on, such as the air. Mr. Marconi sent and received the first radio signal back in 1895. So we've been using these types of waves for well over 100 years now. In a radio situation, the microphone transduces the wave to an electrical signal. So somebody speaks into a microphone, it transduces the wave to electrical signal. That signal goes to a transmitter, which converts the signal to a radio frequency by oscillating the signal with an oscillator. That signal is then sent out via an antenna, thus creating an electromagnetic wave that gets sent across the airways. At the other end, then a receiver tunes into that same frequency and receives the wave. The signal is amplified and sent to the transducer that converts the signal back into sound waves, which then gets sent to the speaker, and we're able to listen to it. So, very similar process from the telephone. It's just instead of being sent across a copper line, a copper wire, a telephone line, it's done over the airwaves. And so the additional component that we need is the ability to an oscillator to create an electromagnetic wave, put that information on the wave, and then at the other end a way to receive it. So with our AM radio and FM radio, AM uses a low frequency broadcasting, so it's lower frequency and is transmitted as ground waves and sky waves, whereas the FM radio is transmitted in the VHS or very high frequency part of the spectrum. The difference though is that VHS waves travel in a straight line, and so you really get about a 70-mile range from the antenna. Which you're all familiar with the fact that you can pick up an AM radio station from much further away than you can an FM. And the reason being is the AM radio, the lower frequency, is transmitted as ground and sky waves, and it'll actually bounce off the ionosphere in the atmosphere and will continue to, if you will, bounce off the ground, bounce off the sky, ground, and so forth, and move forward and continue to travel on. Because it's a lower frequency, it'll do that. Versus the FM radio waves, they won't do that because of the frequency and where they are. They don't vibrate off or continue to transmit off of the ground or the airwaves. So you get about a 70-mile radius. And so, however, the difference is, as you're familiar with, we can put more information on an FM radio wave. And so by doing the frequency modulation, we have the ability to put additional information, much more information, which is why FM radio can come in stereo, meaning two different channels. It's much higher quality and so forth versus the AM. But the AM will go much further. Even here in Kansas, on the right conditions in the atmosphere, that it's not unlikely that you could pick up a radio station up north in, let's say, Minnesota, or even sometimes as far as California in the right scenarios, just because those radio waves will continue to bounce off and travel on. Television also uses electromagnetic waves. Again, just like with the radio, with television we're putting information on, but now not only are we putting an audio signal on, we're also putting a video signal on. And it's transmitted in the very high frequency and ultra high frequency spectrums. Channels 2 through 13 are very high, and 14 through 70 are in the ultra high. When we do television transmission, we're not just doing amplitude and frequency only. Remember, in radio, one is amplitude, one is frequency. In TV, we actually combine them both. And so the amplitude is changed to carry the picture, whereas the frequency is changed to carry the sound. There is more interference on the AM arena, on the AM channels and frequencies, which is why you think about it in the old days. If you ever picked up your television, you talked to your parents or grandparents about it, that if there was a weak signal, more than likely you would get the audio coming through, but you wouldn't get the video. And that's because the video was on that AM frequency, which has more interference, and so the video component of it might have been being blocked, but the audio could come through. Cell phones use the same technology as well, using electromagnetic waves. What we call cell phones comes because the country was divided into cell sites when cell phones were invented, and we divided into cells, and we used a MTSO, or mobile telephone switching office, to basically transfer calls. With the cell phones, we're able to transfer the signal from tower to tower. So again, it's not like an AM signal that'll go a long ways. It's more like almost like the FM, where you have about that 70-mile radius or even less, which is why we have to have so many towers established. But one of the great things about it, as you know, is you could be driving along for an hour, and maybe you might go through three different cells, but your phone call hopefully will maintain. So through the MTSOs, we're able to transfer from tower to tower to tower while still maintaining that phone conversation. As you all, there are times when we drop calls, and more than likely when we drop calls, it's likely because of a malfunction or something going wrong in that transition process. Microwaves are also part of the spectrum. They're the ultra-high part of the spectrum, up to visible light. They travel by direct wave or line of sight as well, and as we talked about in the previous lecture, radar uses the microwaves, and we use this with satellites. And then to end up here, so we have all these waves going on. I mean, when you think about it, at any given point in time, you have all kinds of electromagnetic waves happening all the time. And so it's all about being able to connect. Just depending on what device you have is going to depend on what frequency you're using. So if you have a radio, you switch to AM, you could pick up that frequency. You go to FM, you pick up that frequency. If you have a computer, it has a wireless card that has a particular frequency to pick up a wireless signal. If you have a cell phone, it picks up those signals. So, you know, it's all about having the device that has the ability to connect with that frequency. But at any given point, we have all kinds of electromagnetic waves going around us at the same time. So, with that being said, the FCC, or Federal Communications Commission, developed or assigned frequencies based on the bandwidth requirements of the different broadcasting technologies. And so what the FCC has done is basically identified that these different signals, these different electromagnetic waves, are going to be assigned different frequency levels. So to kind of give you an example here, you can see that the 540 to 1630 kilohertz is what AM radio is, which, if you think about it, when you dial into AM, you either choose a range from 540 or to 1630, as compared to if you're on FM, as you notice over here, it's the 88 to 108 megahertz. So instead of kilohertz and the medium frequency, we're up now into the very high frequency. And as you think about it, when you dial into a radio station, it's anywhere from 88 to 108. And then we also, the TV channels, depending on the height of the channel, the lower levels go from 54 to 216, the upper levels go from 470 to 890. And then we get up into the gigahertz, which gets us into our cellular and wireless. You know, you think about the conversation with your wireless card, it's measured in gigahertz. The cell phone conversations, 2G, 3G, 4G, well, that's talking about gigahertz. And the higher gigahertz, the more information you can put on, which is why the higher gigahertz are faster, you can transfer more data from there. All right, then lastly here, just want to touch a second on another way that we can do this, and that's with light waves, communicating with light, which is called fiber optics. And we're able to do this with high frequency, and we can transfer large amounts of information.